It's a pleasure to have Professor Mert Pesé today with us as our guest speaker. Mert actually got his PhD from computer science, right?
Yes.
From University of Michigan. He is currently an assistant professor of computer science at Clemson University, and he is the founding director of the TigerSec laboratory. What a nice name.
Thanks.
What is the open form, TigerSec?
Tiger Security.
Ah, wow, that's nice. His current research focuses on autonomous vehicle security, adversarial machine learning, and automotive data privacy. He's going to talk about very interesting work on CAN injection. Thanks, Mert. The floor is all yours.
All right. Thanks for having me. Thanks for the introduction. And thanks a lot for having me here. It's a wonderful opportunity. And thanks for being wonderful hosts so far. I really enjoyed my entire time since 10 a.m. Well, today I'm going to give a pretty close version to my job talk that I was giving to a lot of universities a couple of months ago when I was in the job market. It's mostly my PhD work. I'm going to be talking about in-vehicle network security, namely CAN bus security. But before we start, and I'm pretty sure a lot of you, I've talked with a lot of you so far, but what I want to first do is I just want to say a couple of things about myself to people who are online, who haven't met me yet, or who we haven't had a chance to talk to yet. So my name is Mert. As I've said, I'm working on car security and privacy. I'm also going to have a slide at the very end with all my contact details in case you want to reach out to me. I was born in Istanbul, in Turkey. That's where I lived for the first 5 years. I moved to Germany at the age of 5, and I completed all my school education there. I was at a technical university of Munich. I got 2 bachelor degrees in both electrical engineering and computer science and my master's there. Then I spent a year at Audi R&D in Ingolstadt, where I worked for a year and then quit to start my PhD at the University of Michigan in 2017, and I graduated from there this August. Also during my time at Michigan, I worked 2 summers with General Motors R&D, also with Ford Motor Company on certain internal projects within the University of Michigan. And as you can see, I made very bad life choices. I went from the sun to rain to snow. But finally, I had the opportunity to close the loop, and I moved back to South Carolina, where I joined Clemson University as an assistant professor. All right. So automotive security is probably an area you might have heard of. It's very likely you've heard of it like in the last 5 to 10 years, because this is also like the time when it really emerged, to be honest. Especially in the United States, there was a lot of headlines, as you can see. I think the most well-known attack up to date was the GPAC. If you look at the left top corner there, it says hackers remotely kill a Jeep on the highway with me in it. This was the GPAC when hackers could compromise Jeep Cherokees of certain model years from anywhere in the continental United States using a cellular connection, and they could steer the car into a ditch. This was also when people started to take automotive security seriously, to be honest. Before that, it was minor incidents that were patched very fast. And also in US legislation, I think I have an article here. US Senator Markey from Massachusetts, he's trying to push a lot of legislations so that car makers can be made liable for incidents. So it's a growing field. And I really like this slide because a lot of people I'm talking to in computer science, they don't know a lot about cars, except they can transport you from point A to point B on an individual basis. So cars have been out there for a while, developed in the late 19th century by people in Stuttgart, Germany. The last 100 years, cars became more and more sophisticated, but it was mostly on a mechanical standpoint. And after 1990, I would say more and more electronics started to become part of cars. You can think of navigation systems, chip tuning systems, where you can improve the performance of your cars. Then I would say in the last 5 to 10 years, you're hearing more about electric vehicles, but also self-driving cars. This is all what you are partially working on and something that's particularly of interest to you. Now, from an automotive security perspective, I would say the year 2010 was a big year, because that was the year when the first academic paper on car security was published in IEEE S&P at Oakland. So we pretty much had this area of research in the past now 12, 13 years, right, since 2010. And now I made an own taxonomy. So this is how I see this area of research. I would say there's 3 generations of automotive security attacks. There's a first generation attacks. This was mostly people focused on the first 5 years of it, using physical interfaces. We'll see that a lot in this presentation, what I mean with it. So you have a connector under your steering wheel angle. Pretty much every car has it. It's a diagnostic connector that is necessary for diagnostic emissions testing, right? And this is also an entry point into the vehicles and vehicle network. And using your computer, you can connect your computer to it with adapters or dongles. You could start writing stuff into the car. You could make the car misbehave. This was what the first papers really focused on. The thing is, you have to have physical access to a car, and you can only target one car at a time. So it's not a very scalable attack. Now, the second generation of attacks started in 2015 with a GPAC, where, as I've said, hackers could remotely access cars. So they achieved cellular access, but a lot of the research around that here was focusing more on like Bluetooth, Wi-Fi vulnerabilities in the car, vulnerabilities in the IVI, which stands for in-vehicle infotainment, and TCU, which stands for telematic control unit. So IVI is the radio in the car, right? This thing with a touchscreen, that's the IVI. TCU is usually part of an IVI. It can be a standalone unit, but TCU is the unit that has all the antennas in it for Wi-Fi, Bluetooth, cellular connection. You know, a lot of cars these days are connected directly to the internet using an LTE connection. So it's all made possible by the TCU. So vulnerabilities in these units made possible attacks on cars. But again, due to the low range of like Wi-Fi and Bluetooth and these protocols, you could only target a certain number of cars. Definitely more scalable than the first generation, though. And then finally, we have the third generation of attacks, which, again, I made these slides a couple of years ago, and I thought 2020 would be a good year where this could have started. From a security perspective, it's good because it hasn't started yet. But in the third generation of attacks, what we're going to have, and this is one of the areas I'm working on right now, I will talk about that later on during the talk, is how can we exploit vulnerabilities on infotainment units like Android Automotive, that's an up-and-coming IVI operating system, in order to create a malicious third-party app that can directly write to the car thousands, if not millions of cars at the same time. So what we want to do here is that we want to scale attacks to a very large number of vehicles at the same time. And as you can see, with all these generations of attacks, and thank God the third generation hasn't started really yet, but with each generation, attacks become more and more scalable, and thus does the risk and damage potential, and also the liability for car makers. So with this slide, I just want to demonstrate to you that automotive security is still, I would say, a toddler, or maybe like a teenager. We're still in the second generation, to be honest. It's going to get even more and more important. And I'm not even talking about factors that could affect autonomous vehicles at this point, right? This is just for traditional vehicles, electric vehicles, you know, the ones that do not have these fancy self-driving capabilities. So yeah, if I considered that, it would be even worse. So, but all these attacks, all these 3 gens of attacks have something in common. So this is a slide I made in the year 2015 when I started working on car security. Overview of all the incidents that have happened this year. You have some first-gen attacks like the dongle attack here, where you have to actually physically plug this into the vehicle. You have some second-generation attacks like remote car door unlock from BMW. They hacked BMW's connected drive backend. Then we have the GPAC here. This was the biggest incident in the state. 1.4 million vehicles had to be recalled. Cost them a ton of money because you have to get the cars to the dealer, flash a new update, and this costs money, right, to everybody involved, especially the car maker. So It was a huge thing. And actually, this is a picture of the article when they published this attack, this white paper. This was a car attack, the Jeep Cherokee, right? And when the car was going on that beautiful road, they could literally steer it 90 degrees to the left and drive it into a ditch. So yeah, it was dangerous. All these attacks have one thing in common, and this is it's a thing called CAN injection. This is the necessary final component for all the attacks, and this is what this talk is going to be about. What is CAN injection? We're going to talk about it, and we're going to learn about challenges and solutions to this problem in this talk. So let's break up the word CAN injection, shall we? So CAN stands for Controller Area Network. It is a protocol like TCP/IP that you know from local area networks. It is a broadcast protocol, so it's not like it does not have a sender and a destination. So if ECU-A wants to get some information over to ECU-B, it broadcasts a message with a CAN ID. So the CAN ID is here. It's a message identifier, and everybody who's on the bus listens to it. But if only ECU-B is interested in it, it will take in the message and process the payload, the data. But others will just discard it because they don't care about it, right? So there's no sender destination. There's just one message identifier, and it's broadcasted. So it's multi-master. There's a ton of these ECUs on the network. They have to figure out a way how to arrange whose turn it is, who is allowed to broadcast in the bus, because there's no time frames where you're supposed to send. If ECU-A says, "Oh, I want to broadcast a message, and I just need to get this message out," it needs to wait its turn, and they have in the CAN protocol, they have an arbitration protocol how to do it. But what I'm trying to say here is, from a security perspective, this is that. This was developed in the late 80s by Bosch in Germany, and I think the recent standard was passed in '93, if I'm not mistaken, and hasn't been touched since. It's still being used in cars. Of course, now cars also have automotive Ethernet and a lot of more advanced protocols because they need higher bandwidth for camera data, LiDAR data, and so on and so forth. But for control data, this is still the de facto protocol and does have zero security. So basically, an attacker that gets on the CAN bus can read all the messages because they're in plain text, they're not encrypted. And it also can impersonate any sender ECU. So if I'm on a CAN bus, and if I'm the attacker, I can say I'm ECU-A because the only thing I have to know is what message identifier I have to use. You can figure it out. You can eavesdrop on the bus, right? Because it's not encrypted. So you can figure out what ECU-A is sending, and you can impersonate ECU-A by sending messages on its behalf. And you can even override the data that ECU-A was supposed to send. So from a security perspective, this is literally the worst case possible. I'm not even talking about denial of service attacks. It's even easier than what I've just described. So one more thing, we have to understand how the internals of a car work. So this is an in-vehicle network architecture. This is an architecture that's commonly used by a lot of car manufacturers. There are some recent shifts because of bandwidth requirements, but a lot of cars still use that. So you have a central gateway, you have different domains. So you functionally group ECUs together. So powertrain, for example, has stuff like engine control, transmission control. Body can have ECUs for pretty much everything what you can see in the car which you can press, like AC, doors, windows, right? All that stuff is considered body. There's also different protocols like MOS and LIN that are used, but CAN is a de facto standard. And these are all interconnected with a central gateway, and then you have this miraculous thing called OBD2. This is the diagnostic connector I was talking about that's under your steering wheel, and that all cars actually have these days. And this is an entry point that the first generation attackers were targeting. So from an attacker perspective, again, if you want to get access into the CAN bus to do all the shenanigans that I've described here, you have two access points. First one is obviously OBD2, right? This is what the first generation attackers did. And then the second generation attackers were using vulnerabilities and infotainment and telematic control unit ECUs. So they were remotely compromising like an ECU that had wireless capabilities to the outside. From an autonomous driving perspective, it's also possible because they will basically compromise like ADAS ECUs or ECUs that take in data from like the exterior environment. Okay, so CAN bus security properties. So whoever has taken a core security class knows that there's the CIA triangle, which can be extended. So the first one is authenticity. Authenticity means that, and I know a lot of you are not security people here. That's why I spent a little bit more time on the security basics here. So authenticity means, is it coming from like a legitimate person or a legitimate entity, or is it like impersonated? And since we do not have any notion of who's really the sender, because anybody who has access to the network can basically send messages, broadcast messages with the message ID of the original one. This is a problem. So impersonation attacks. Integrity. Integrity refers to, is the data that I'm sending, and we have 8 bytes of data in CAN, is that being spoofed or not? There's no mechanism to detect tampering. Usually you can use message authentication codes to solve that. Availability. Denial of service is super easy to conduct because of how the CAN protocol is designed. I'm not going to go into detail here because it's not part of this talk. And the latter is confidentiality. We had this already. All the messages are sent in plain text, so anybody can listen and log the data and be able to read them. Okay, great. So now let's continue to CAN injection, to the injection part of CAN injection. So what we want to do is we want to form a well-crafted CAN message. We want to know which message identifier to send and what data to send in order to achieve something like this: steer the car into a ditch. We want to break the vehicle's functionalities, right? We want a car that's going straight. We want to be able to turn it 90 degrees to the left. So in order to affect the steering wheel angle, for instance, we have to know, okay, so which CAN ID or which message identifier is going to cause a change in the steering wheel angle? We have to know this. And then also we have 8 bytes of data. You've seen the CAN message format on the previous slide. We have 8 bytes of data, and we need to know actually like how to encode this data in the payload in this data field in order to achieve this goal. And this is an example. So 8 bytes of data, right? This can be, for example, message identifier 100. And we have multiple data also within a message. So this can be speed, this can be steering wheel angle, this can be RPM, this can be whatever, you know. And the thing is, this is not a unique standard. It really differs from car manufacturer to car manufacturer, even among different vehicle models and years within a car manufacturer's lineup. It really changes. So these semantics or these translation tables where this information is located within the data is proprietary. OEMs do not disclose it to the public, mostly for security reasons, because if you actually knew where stuff is, you could perform a CAN injection attack much faster. Yeah, so security by obscurity, that's what we call it in the security community. You want to keep something obscure, something hidden, and you hope that nobody's going to target it. Okay, so now CAN injection usually focus on these 3 CAN bus security properties, or research to prevent CAN injection attacks. It looks very straightforward because these 3 security properties are not available. They do not exist on the CAN bus, but usually there's an obstacle, and this is what I just mentioned. These semantics, these translation tables are kept proprietary. So OEMs are car makers, by the way, they think that, well, attackers, since they do not know the message format, the semantics, they're not going to be able to achieve it. But, well, is there really? And the thing is, anybody who wants to break something, who has the will to break something as a hacker, is going to achieve it. It might be a little bit hard. They might have to put a little bit more effort than usual into it, but they will be able to achieve it. And what you can do is, since everything here is in plain text, you can log enough data and figure out what is what. You can reverse engineer the logic of it, and basically launch a CAN injection attack after that, especially because there's no way for you that's hindering you, right? Because there is no message authentication codes. There's no guarantees of who is sending the message. You can impersonate any ECU. So it's very straightforward. And in this talk, we're going to see how all these 4 security properties lead to CAN injection attack and talk about why it actually matters. So the first thing is, what we've figured out so far is, because of the lack of confidentiality, because the messages are not encrypted, we can enable CAN injection attacks by reverse engineering. And the question is, how serious is the threat of reverse engineering, and how can injection be prevented? For example, the Jeep hackers spent multiple weeks in order to figure out the semantics. For reverse engineering, they spent multiple weeks. Only for the Jeep Cherokee, because for other cars, they would have to start from scratch again. We'll talk about in this work, in the first chapter, how we can automate it for any vehicle. Automated pipeline where you collect a bunch of data, throw it into the automated model, and then you basically generate, reverse engineer all the data that's possible for any car, for any given car. One thing I want to talk about before I start my talk is what I've worked on during my PhD. I worked mostly on automotive security and privacy. So from a security perspective, I worked on, it's mostly CAN. It's mostly CAN about security. We're actually going to talk about the first two papers here during this talk. I also worked some on car-to-car communication, V2V, vehicle-to-vehicle communication security here. On automotive privacy, I have an interesting work at PETS. It's a premier privacy venue. Maybe some of you are familiar with it. Where it was an interesting paper. It was mostly a data science paper. So where by collecting steering wheel angle, we showed that just by collecting steering wheel angle data from a car, we could actually infer the location data, the route that the driver took. And it's actually pretty straightforward if you think about that. The steering wheel angle is highly correlated with the road curvature, right? Because you steer, however, the road is curved usually most of the time, except you're on a grid. And you can match the road curvature, which you can infer from like OpenStreetMaps, Google Maps, whatever, and basically do some matching. We use dynamic time warping, for example, if you've ever heard about that technique, in order to basically do like a search on a certain area. And it was actually fairly accurate as long as you knew kind of like the neighborhood or the area you're in. So this was a data science paper mostly. I've a lot of the other projects are really like work that I've conducted with car makers because of GDPR. Now everybody wants to cover their asses, and they wanted to see, okay, what vehicular sensors are really dangerous, and what should we collect, what should we not collect. Let's have a privacy framework for data sharing, for the data that we're collecting and sharing and selling to advertisers and other third parties, and make sure that we're GDPR compliant, or CALOPA compliant, which is a California version of GDPR. Right. All right, we're going to focus on these two works here. And without further ado, we'll start, but we're only going to cover these three. Properties availability is this third work, Michigan, that I had there. It's still under review, so I shouldn't be talking about that in a public talk, I thought. And specifically, these the first two works that I've mentioned are going to cover. The first question is, how can we accelerate reverse engineering? So this automated reverse engineering pipeline that works for all the cars. That's going to be the first work here, LibreCAN. And the second question is, okay, now that we've seen that reverse engineering is easy, CAN injection is actually trivial to perform, how can we defend against CAN injection attacks in a practical way? We're going to try to break away from traditional concept and look how to satisfy automotive requirements, automotive constraints at the same time. All right, so LibreCAN is the first work. So we've seen a slide before. The solution, as I've said, is either you spend weeks and do some manual reverse engineering. So there's a lot of tools. These are Linux tools, open source, and you connect USB to OBD adapter to your car and the other end to your laptop, and then you can run these cool Linux tools, and you see the CAN message. Right here are the timestamps. These are the CAN message IDs, the message identifier. They have like 8 bytes of payload, right? And you can even see which bytes or bits are flipping. There's a lot of really good tools. And then by basically pressing some buttons in the car and looking at what flips, you can figure out what's really what event is really encoded in what message and in what position. Takes weeks, depending on the scope of what you want to reverse engineer. Some of that stuff might be really hard to do it manually. And we thought, okay, let's just design a pipeline. We're going to log a bunch of data. So somebody's going to be driving normally, like they are. We're going to connect some cool tools to their car, and it's not going to disturb them while driving. And then we're going to take all this data and throw it into like a pipeline here. And then it should generate us in a couple of minutes, like a really good, cohesive translation table of all the car's information. And we're going to talk about that. So this is the way not to do it. This is the way to do it from now on. Right. So first question is, okay, what data is really in the car? And this might be actually really interesting to you too, since some of you are working on cars, and if you want to especially design machine learning models that are more robust to adversarial attacks. One way I proposed, and we're going to talk about that later, is to use side channels. Just don't feed only the computer vision models data directly from the camera or like from the LiDAR or the radar, but also use in-vehicle network data to make it more robust. Use some correlation, for example. In order to do that, in order to understand like what's available in the car, I actually have a cool overview here. So broadly speaking, there's two categories of data in cars. There's powertrain or kinematic related information. So that's everything that's related to the motion of the vehicle. So, for example, the speed of the car, right? That's the battery voltage, engine coolant temperature. This is for gasoline, diesel cars. For electric cars, it's a little bit different. Torque is something that all the cars have. Engine RPM. That's the second thing on your dashboard. How fast your engine's going. Also, by using like phones inside cars, you can get a lot of information about its acceleration, gyroscope, the compass, the direction it's going by using IMU sensors and phones. And then the second category of data are body-related information. So body is everything that in the main driver cabin, all the buttons you can touch, AC, windows, door locks, mirrors, seat belts, turn signals, all that stuff. So these are mostly the two categories of information. There's other information in the car that are used internally for network management. Then there's emergency call stuff, but these are not available on all cars, and these are also usually stuff you do not collect or cannot collect. It's used only for internal purposes and are not really important for you. So, but the question is, why these data? Like we have 24 signals here and 53 events that we defined here. And this covers, by the way, a lot of the cars we've looked at. Obviously, like some more sophisticated premium cars generate more data because they have features that, entry-level cars don't have, but mostly it's these data that are also used in a lot of academic papers. But the question is, why these data? Like, why exactly 24 and 53? It's kind of random besides, that all cars support it. In order to understand it, we need to look a little bit into automotive data collection. And this is quite interesting if you ever want to work on a real vehicle and collect data out of it or do anything with it. This is the diagnostic connector that is available under the steering wheel that I was talking about. It's mandated in all cars that are sold after 96 or produced after 96, at least in the US. I think in Europe and Turkey, it's 2001. So except you're driving an old Tofaş, you shouldn't have a problem finding this thing. It's used for emissions testing, right? So that's why it was introduced initially. And we also saw in this in-vehicle network architecture diagram that it's one of these main entry points into the network to access the CAN bus. So and then there's something called the OBD2 protocol, which should not be confused with the OBD2 interface. The protocol is it's a standardized higher layer protocol that's used for emissions testing. So you can actually obtain certain information like speed or RPM directly through it, and it's like standard for all vehicles. Like you can say, I want to know the speed of the vehicle at this point, and it will return it to you. But it only supports like very few parameters that are mostly related for emissions testing. I've told you car makers use proprietary standards to encode their data, and they do. They still do it for speed and stuff, but besides that, there's certain data like speed and for example, the O2 sensor and some, I don't know, I'm not a mechanical engineer. For all that stuff, they need to support this OBD2 protocol as well. And the tooling that we can use for that, so this is the OBD2 connector. It's under the steering wheel, as you can see. There's dongles here that you can use. The blue ones are actually as cheap as $3. There is also USB to OBD dongles that are more like $300. I know these prices very well because I had these dongles and I broke the one that was wired and expensive, and I got yelled at by my advisor. So yeah, I kept using those dongles after that. So these are $3. And if you want to like connect multiple tools at the same time, you can use like a Y cable, like a splitter for that. Okay, going back now, why this data? So all these data that you see here in light blue are included in this OBD2 protocol, or the vast majority of them at least. And so we can use the OBD2 protocol because we know the absolute values as a side channel to figure out wherever it is on the canvas. With the OBD2 protocol, you can get these absolute values, but you're not allowed to write to it, right? You cannot say, oh, I want to write speed 70 to the car right now. You can only read it. If you want to write to it, you need to know the CAN ID and the position in the data payload in order to inject it. You don't need to know the encoding, but you can use the OBD2 side channel, the absolute values from it, in order to figure out which CAN ID is located in. And when we can use a phone for some additional sensors here, and then for the OBD2 protocol, we can use Lugano to collect data. Okay, and for the second category of information for the body related, what we can do is we can define these 53 events. We can give participants Android phone, and we can say open, or open the hood, find the button, press it, and then I've shown you that tool here, where you can see the bit flips. They can be like colored in red too, right? And instead of inspecting it with a human eye, we can automate this process. We can see automatically where a bit is flipping, and we can try to exclude messages that are not related to this event. So by smart CAN filtering, we can actually narrow it down. Okay, so how are we doing it? So we have two major phases. So for pneumatic related information, powertrain related information, we have phase 1, and for body related information, we have phase 2. Phase 0 is a pre-processing stage that we have that is mostly doing signal extraction. So signal extraction, I've mentioned briefly, or I've shown you this. We have multiple signals within one CAN message, within one CAN ID, right? This can be the speed, this can be steering angle, this can be the RPM, right? And all the areas that are not shaded or not colored are empty. There's nothing there. It's a bunch of zeros all the time because there's no information. So what we need to do, though, is when we get the CAN messages, we need to figure out where the signal boundaries are. For example, 0 to 15 bits, right? Or this would be 32 to, I think, 32 to 44 or whatever bits. And there's multiple signal types. I'm not going to go into detail here, but we're interested in physical values. So if there's counters and check codes, we need to figure out that these are not physical values and delete them or discard them. We also defined a lot of design parameters in this stage in order to optimize the accuracy of this project for as many cars as possible. The second thing we do in phase 0 in this pre-processing stage is coordinate alignment. So we have a smartphone that we use as an additional side channel. So what we need to do is we need to make sure that the coordinate systems of both the car and the phone are aligned. So there's some rotation matrices involved. So some simple linear algebra math. Okay, then phase 1 is reverse engineering powertrain related data. So now here we have the extracted signals from phase 0, and we have our side channels, for example, from the OBD2 protocol. So since the OBD2 protocol yields you the data at, I think, 10 hertz, and the extracted CAN signals can be anywhere from 1 to 100 hertz, you need to make sure that they're sampled to the same length first. So you have to do some resampling in the beginning. And then there's a really interesting fact that the CAN signals, the way they're encoded in a CAN message, is in a linear relationship with the absolute value. So if you're going 100 kilometers per hour with a car, it might not be encoded in a signal in binary as 100, but it might be like 50 with a scale of 2 and an offset of 0, right? So there's a scale in the offset that needs to be also known to properly encode it. But since there's this linear mapping, what we can do is we can run cross correlation between the extracted signals R and the side channel Z. So for example, for the engine RPM, let's say we're interested in knowing where the engine RPM is located. Run cross correlation with all the extracted signals. So we have, I think, 1,000 or 2,000 signals per car usually. So it's fairly quick, because it's cross correlation is not a very heavy operation. And then we're going to sort it descending with the highest correlation score first, which then says that the Kennedy 516 from bit position 28 to 39 had a correlation score of almost 98%. So it's very likely that this Kennedy during these bit positions is engine RPM. So if you want to modify, if you want to spoof later the engine RPM, we will know where to inject this message, how to craft the CAN message. 1071 also has a high correlation score, so probably related to, but then it's going to drop after some point. And we need to define a cutoff point where we can say everything above this line is going to be related to engine RPM, and everything below is not. And there's also a design parameter involved in how to draw this cutoff point. So this is just an example. It's not necessarily where we drew it for that, just for visualization purposes. And then finally, linear regression can help us to figure out the scale and the offset. Okay, cool. Phase two. I think this is the most interesting part of it. Reverse engineering body-related information. So we have 53 events, like open the door, passenger, turn on the heat, setting 1 in the car, and so on and so forth. We developed an Android app here where we define all the events. And basically, it says something open front, you do it, then you click next event, and so on and so forth. And it loops you through all 53 events. Another thing that we reported as our baseline for our car is a reference snippet. The reference snippet is when you're not doing anything in the car. So the engine is off, the ignition is off, right? The lights are off, AC is off, you're not pressing anything. You just have to have accessory power on. So the key has to be turned on once. So you have power in the dongle to collect the data. But everything else should be off. This is our baseline that we're going to compare to. Because now what we're going to do, the 3 stages, we're going to eliminate messages that cannot be related to this event. First thing is constant messages. If you have messages that never change while we report this event of opening the trunk, for example, it cannot really be related to opening the trunk, this message, right? Because it says constant, and we actually do something related to it. So this is the first stage. The second stage is reference message. So the reference snippet was when we're not pressing anything, when everything is off. And if it still stays the same, and we're opening the trunk, so we're performing an action where we expect something to flip, that message can also not be related to this. It's very intuitive, actually. And the third stage are powertrain messages. So these are IDs that we identified from phase 1 that are related to the speeds and engine RPM, steering wheel angle, and usually body-related and powertrain-related information. I told you these are 2 categories of data. They're usually never encoded in the same CAN ID. So we can assume that if we see CAN IDs from powertrain messages, that these are not going to be really related to the body-related event, like opening the trunk. So we can exclude those as well. And we optimize obviously the order of these 3 stages in order to get the maximum performance. And we had another 2 design parameters to tweak the performance of our algorithm. Okay, in our setup, we use 4 cars, same manufacturer. I can't name it, we have an NDA, American car maker. 4 cars, sedan, or compact, I think it's called compact SUV, premium SUV, pickup truck. So in order to test if our algorithm is working with different complexities of cars, because obviously this car has more functionality than this car. Okay, so evaluating phase 0. What we tweak these design parameters here, as I've said, to maximize the number of correctly extracted signals. There's 2 takeaways from this phase, from the signal extraction phase. So more than half of all the signals can be reverse engineered at all. And now you're going to think this is a very low number, but there's a lot of signals that we can never really trigger. Like I told you, there's some network management stuff that are usually not locked or that's usually not triggered. Emergency call is something that is activated to get into an accident, right? A lot of cars have it now in the US. I think the new cars in the US have to be by law equipped with it. So if a collision is detected, it automatically dials the police and probably the police, 911, right? It's called emergency call. And we did not damage any of our cars while recording this data. So obviously it was not there. So it's mostly that stuff. And these are actually more than you think. So we confirmed these numbers with the car maker that we were working with. And they confirmed that these numbers make sense. So that, this is the number of the number of signals that we can trigger in normal driving conditions. And the second key takeaway from the slide is that matching the exact signal boundaries is difficult. So you only match like around a quarter to a third of all the signal boundaries correctly. And the reason for that is also very, very easy to explain. And probably it's not the best metric to define, to be honest here. So, for example, imagine a car that has an 8-bit signal for speed, encodes data from 0 to 255 kilometers per hour, right? In the US, the speed limit is 70. That's 110, 120 kilometers per hour. So, and we draw that speed limit because the last thing I want to do is getting deported from the country by breaking laws. So what happened is we never drove past 120 kilometers per hour. So the most significant bit never gets flipped. It's always 0. So we could never experience the entirety of the range. Same for RPM and a lot of other things. And that's why these numbers might look low, but we also had another metric that's in the paper, it's not shown here, of nearly correctly matched boundaries, and we had 90+% performance there. So numbers make more sense in that case. So we had a problem with the MSBs of certain signals. Okay, and then in phase 1, we had these 4 vehicles again, precision recall curve, and then we can say that most of these signals are correct. We had trouble with certain signal groups that in future iterations of this paper were actually tweaked by other researchers. The other thing I want to say about this work is this was the groundbreaking work in automated reverse engineering. So from 2019. So after us, a lot of researchers took this, improved it. Also, this work is used by researchers on 4 continents right now in many universities. It's not open source available, only by request. So I know actually who I'm sharing this with. And it's actually used by a lot of, and cited also by a lot of researchers who use this tool for security research. And these numbers are much better with future iterations. Obviously, I allow them to tweak this algorithm and make it better. So these are just my baseline 2019 numbers that are much better now. Okay, phase 2 is getting these numbers down, filtering messages for certain events. So we can see that we have like almost 110 messages that you can always log. And after applying these 3 stages of filtering by eliminating messages, we see that at the end we're around 12, 13, 14 messages. So we reduced it by quite a lot. Out of these, let's say 12, 13 messages that we have at the end, still, not all of them are related to really that event of opening the door, for example, maybe only like 5 or 6 might be, but we still reduced it by a lot. And there's still some manual effort needed at the end in order to narrow it further down. But what we can say is it's very accurate. And obviously, these numbers are not something you're used from your field, from computer vision, where you always want to see 99+.9% plus. But these were pretty good for the security community, obviously. And the key takeaway is you can reduce the number of KNIDs by more than 10 times, which saves a lot of time in order to narrow it further down by human effort. Other metrics we looked at is actually how much data do we have to collect to throw into this algorithm so it can actually work well. We collect a bunch of data, but we tested all these numbers that you saw with 1 hour data. With longer data, it actually got a little bit better even, but not too much. And we found that even using less data, 30 minutes of data that you collect by just driving freely around, you can do a pretty good job at getting the same numbers as we do. For phase 2, this is the body-related stuff. We had this Android app that you could use to record the data. We gave it to people who never drove a car. We gave it to like experienced drivers. We used, I don't know how many human subjects we had. I think more than 10. And we calculated the average of how long they took in order to swoop through these 53 events and record them. And it took them around 10 minutes on average. So what we can say is by 40 minutes of human effort, you can actually run LibreCAN, and LibreCAN is really fast. Once you throw in the data into the pipeline, we had like a medium-sized setup. And I think it was a good setup back in the day. We saw that under 2 minutes, in a minute and a half, we could reverse engineer all this data. So to sum up LibreCAN, we show that the car hacking barrier can be overcome by automated CAN bus reverse engineering. It's the first framework that's fully automated, as I've said, and it's used by a lot of people now. There was some partially existing related approaches, and it was much, much better back at the time. And also it's very fast and very convenient for a lot of people. Even like on laptops, I think it takes less than 5 minutes. So It's because it's not using any sophisticated machine learning. It's purely statistical based. All right, now that we've seen that can injection is getting super easy because everybody has access to tools like LibreCAN, we want to see how to defend against these can injection attacks. And if I'd like to explain this joke, especially to international audiences. This work is called S2 CAN, okay? And it stands for sufficiently secure CAN, that's why S2. And this bird here is called toucan, S2 CAN. So when I made this joke in America, they were like, okay, I'm Captain Obvious. But, you know, for international audiences, I like to keep that joke. Okay, so I promise you this is the last time you're going to see this slide. I think it's the third time, but promise it's the last one. So the problem what we've seen so far was security by obscurity is a current standard. You do not disclose these translation tables, and car makers think, okay, nobody's going to hack our cars because there's a ton of work to reverse engineer it. But well, you know, you can automate it. This is what we show with LibreCAN, right? So, and the thing is, if you encrypted the payload, when you log data and it's encrypted, there's nothing you can do. You can't reverse engineer anymore. So encryption technically is a solution to everything. But why is nobody proposing this? Or I mean, I'm pretty sure somebody has thought about encrypting the payload, but why is no car maker adapting it? Why is nobody still using it? I mean, this is a known problem, right? Well, in order to understand that, we need to see what's out there from a CAN security solution perspective. And there's papers that go back to 2011, way back to 2011. This looks like it's been published in 2000. It's not. I don't know why the reference is encoded like that. Google Scholar messed up something there. But a lot of solutions here. Mostly are focusing on authenticity, basically trying to prevent impersonation attacks. And there's a lot of hardware, software solution, and you can see like the performance metrics that they have evaluated or that we have done for them. There's three problems associated with all these problems. So first one is cost, and this is really important to understand to you. Car makers are cheap. They hate spending money. Their profit margins, their operating and profit margins are very thin. So if you buy a $20,000 vehicle, how much do you think a car maker makes money from? Like profits from the sale of the one car? Just guess. Wish. Lower, much lower. It's usually around $1,000.
Wow.
That's what they profit. So what they sell millions of cars. So that's where they make the money. They have this economics of scale. They sell a lot, but they don't make a lot of money. Even if they make 5 to 10% money, I think the average is like 7 to 8%. So I might have underestimated with 1,000, but you get what I mean. It's not a lot. And if they add now fancy controllers because they want to add some security features to that, even if it's like $10 per car, that's a lot of money they're going to lose out on that. And it's nothing they can really advertise or sell because security is something you implicitly expect in your car. It's not something you advertise to the audience, to your buyers. So, and a lot of ECUs in cars are resource constrained. So let me give you an example of some engine control unit specs. 1 megabyte of flash storage, 64 kilobytes of RAM, couple megahertz clock, a couple megahertz, more like 80, 100 megahertz. So one example, I'm going to give it to you. I'm going to give you this Toyota Corollas, Camrys, nice cars. The engine control unit they're using in their current models is the same as 10 years ago. Why? Because it's the same thing. The engine needs to do certain operations to work, but there is no advances in the software anymore, and it's still doing the same job. And if they want to switch to a newer platform, they have to like redesign the entire software. Actually, Toyota or any OEM is not doing the software in-house, but there's a supply chain for it. They source out the job to a company like Bosch or Harman that does the job for them. And they have to get recertified for every software they do because of some safety compliance things, laws. So it costs them a lot of money, and they do not change existing hardware. Okay, so if you want to add some security features now, like encryption, decryption, it's going to consume CPU cycles, right? It's going to add to the latency, which is a huge problem. Because if you expect a message to be received at the receiver within 10 milliseconds to operate properly, if you want your brakes to work, then it needs to be there at 10 milliseconds at the brake. But now if you encrypt and decrypt that thing, you're going to add overhead latency. You have hard real-time requirements. If you miss it, well, you might die. The driver might die. And you also need to get, for compliance issues, you need to get recertified with ISO 20s, with an ISO standard for functional safety. It's a whole mess. It's a complete mess. So that's why nobody's like really using security. Another thing is bus load. I'm not even going to go into this right now because it's not super important, but you get the gist. There's automotive requirements, and now these academics are like, oh yeah, we're going to use message authentication codes, and we're going to use encryption. We're going to whatever we know from traditional networks, from IT networks. We're going to throw everything inside the car network. It's going to work. I mean, it's secure. It's going to work. It's going to work somehow, but not really in a car. So that's a big problem. And what we thought, okay, secure kind is fantastic. It's great, but it's not really practical. So why don't we come up with a solution where we do not use traditional crypto-based solutions, because these are too heavy for cars. We address these three key feasibility issues, and we offer still a good level of security, because right now the option is you have zero security, or you have amazing security, but you can't really put it into cars. So we propose a trade-off between performance and security with SUCAN. And one metric that's a little bit, not green here, everything is perfect otherwise from a performance standpoint, but from a security level, we only have 50-bit entropy, which is below what's really proposed these days with 80 bits, but we show in a security analysis that it's still good enough. It's sufficiently secure. We're not claiming it's absolutely secure. Still better than no security at all. Well, how S2CAN works is this is a minimum working example from the unequal network architecture. So we have a gateway, which is the entry point for OpenE2. We have two slave ECUs here. This can be a car train CAN, for instance. And what we do is we introduce a logical ordering, 1 and 2. Can be done at manufacturing time once. And for each of these slave ECUs, we generate 3 parameters: internal ID, position, and the counter. We use the ID and the counter to define a 2-byte long integrity parameter through this arithmetic operation. And then we use the position information to squeeze this into like available space in the payload. So you see all these gray areas, as I've said, are available. It's a bunch of zeros not used by anyone. So, and we need at least 2 bytes here to squeeze it in. And internal position is going to tell you like where to squeeze it in. It's a random parameter. We can, for example, squeeze it like this. And we analyze also a bunch of cars for available space, and like most cars, I think over 80 or 85% of CAN messages actually have at least 2 bytes of space. With some further rebalancing techniques that we suggest in the paper, this can actually be brought to above 90-something%. And the reason we're defining this integrity parameter is this is something we can use to authenticate that it's coming from a legitimate ECU. An attacker would need to, besides reverse engineering all that signal stuff, need to also figure out this random parameter that changes once in a while, and depends on the ECU. And finally, we have the encoding parameter. This is generated by the gateway, by the master ECU. It's an A tuple with 8 values, right? A tuple, and each value can be a number from 0 to 7. And basically, this is our getaway of doing encryption. It's actually not real encryption, because you know how encryption works. It's super complicated and secure. This is a way of obfuscate the payload. So let's say this is our payload. So, and we have an encoding parameter of 3 to 1. That means that the first byte here will be shifted 3 to the left or 3 to the right. The second one will be shifted 2 to the left. It doesn't matter if it's left or right. You just have to be consistent throughout the entire way. And basically what happens is you shift this, let's say 3 to the left, this 2 to the left, this 1 to the left. You get the idea, right? You create some random obfuscation here. It's not really encryption. It's like some way of encoding the information. And this is for confidentiality protection. So as an alternative to encryption. Now the question is, we have these 4 parameters that are very important for this to work. How do we get it? We get it by a handshake that's periodic. We're going to talk in a second about why it's periodic. But a handshake is basically a 3-way handshake. So the gateway sends encoding parameter to the slaves. And in its step, the slaves then send out the internal ID and counter respectively, and then the gateway acknowledges it that this process is done. Now, an eavesdropper might, of course, this is not encrypted. This entire thing is not encrypted or authenticated. They might spoof it, they might alter it, they might eavesdrop on it. This is something we do not want to do. That's why we say for these 4 messages in this case, we need to make sure to use proper cryptography like AES and HMAC, SHA-256, to both authenticate or both secure the integrity and the confidentiality of these messages. And then you're going to say, okay, well, you said we want to break away from cryptography. We don't want to use it. But here's the thing. This is 4 messages. Usually in a CAN bus, you have 100 messages per second. And if you only do this once in a while, this handshake, if you repeat this handshake once in a while, the amount of messages you're going to encrypt, and this is not really safety critical either, this can take time, doesn't matter, is much better than actually doing it for every single operational message. And this is where we use some crypto, only during the handshake. And this is periodic, because what if these parameters can get cracked or can get reverse engineered at some point by the attacker? We want to prevent this by saying we will regenerate these parameters in a random way, maybe every 5 minutes, maybe every 10 minutes. We'll see on the next slide how long it's going to take, and then repeat this handshake process for security. So from a benchmark perspective, we actually use a real card too, but these results are reported on some Arduinos that we use. The handshake's pretty fast, takes less than 2 seconds after you start your car. And this is a latency. I'm not going to go too much into it because of time mostly. And SU-CAN only has an overhead of 75 microseconds, which is 44 times faster than the next best approach. And 75 microseconds overhead is basically nothing from a CAN scheduling perspective. So, and we also looked at memory requirements, like how much RAM, how much key storage we need in the flash and stuff. Much better than what else exists out there. Now, this is the last content slide, and I'm going to start wrapping up this entire thing because we're also, when do we have to be out here?
We have this other event here, right, Burak? Okay.
When is it?
We can wrap it up in 5 minutes, 5 minutes maybe. We can give a break about
5 to 10. Okay. I'll try to wrap it up. I'm not going to go too much into the security analysis here because I think you're not super interested in the security. But what I'm trying to say here, the important thing is you can use the tool from before, LibreCAN, modify it a little, and use it as an attack tool. Because the thing is, now we obfuscated the message a little bit by shifting stuff. And now we want to reverse engineer and see if we can get this data out again. It's a little bit harder, obviously, but by modifying LibreCAN, we actually added some multi-threading to make it smarter and faster. We can try to crack the encoding 400 combos. We can then need to find out the counter position and internal ID, this integrity parameter, to authenticate it correctly. And these are the results here that we also conducted, same for vehicles as before, with different lengths of recording time that we threw into LibreCAN. 60 minutes worked pretty well, except for vehicle D, nothing worked there. And less than 15 minutes of data to throw into LibreCAN Plus was mostly a problem. So we said, okay, we need at least 15 minutes of data that we need to collect before starting our cracking operation. And to be honest, the entire attack time, if you think about it, is the time to record the data, the minimum amount of data you have to give to the algorithm, the time to crack the encoding, and the time to authenticate correctly. This time is negligible, so it really comes up to the recording time and the cracking time. And now we can say we have a session cycle. This is how frequently we repeat our handshake. If our session cycle is smaller than what the time that the attacker needs, well, then this can be secure. So if you generate new parameters before the attacker is done, figuring out what our parameters of that session is, we're good. So we need to basically figure out how large this attack time is. And well, we need at least 15 minutes for good working. These are the times for cracking the encoding. And if you add this up, we can say that our session cycle, the max our session cycle can be, is around 18 to 20 minutes. The smaller, the better. Because some attackers have faster computers, and there's still a minimum bound of 15 minutes, to be honest. But if you say LibreCAN Plus is optimized, works on less data, you can make it as small as possible, even a minute. And it's still from an efficiency perspective and a security perspective is really good. Okay, so to wrap up SU-CAN, What we care about here is a secure CAN bus, at least some level of security and practicality. And we introduce a security performance trade-off. So from a feasibility standpoint, it's the first really secure CAN approach that looks at these automotive requirements that I've mentioned. This was also done in work with General Motors. So, they gave me like these are our requirements. These are the reasons why we don't have a secure CAN bus. It's performance. It's actually really, really fast, obviously, since it's not using crypto, and it's also secure as long as the session cycle is chosen correctly. So to conclude this talk, CAN is still something that's widely used. It's still a de facto protocol, no security whatsoever. It leads to CAN injection attacks, which affect human safety. You can steer the car into a ditch, right? And we address two aspects here of this CAN injection, namely how we can accelerate CAN injection attacks by automating reverse engineering, and how we can prevent it in a feasible and practical way. So these are the three security properties that we looked at. And other works that I've written and that are under review still is how to protect like availability, like DOS attacks, to close a loop of all security properties in a CAN bus. So I've solved all CAN bus problems. Hopefully, we never have to work on that again. This is the slide that I think most of you are looking forward to. I need another 2 minutes, and then I'm done. So what I'm currently working on. This is something probably you're not super interested in. Android Automotive, I've told you, third generation attacks. This is the new operating system that's in your radio. Questions are, which vehicles are susceptible to these third generation attacks? So this is more like a production study analysis. We get different cars. We look at how to launch CAN injection attacks on these cars. This is a project I'm working on right now that is really cool. Google is collecting data from your car. If you run Android Automotive, your car maker is collecting data from your car. What data are they collecting? Are they violating GDPR because they're not putting stuff in your privacy policies? We found some really screwed up stuff. So this is really cool work. Google hates me for doing this, but well, at least I know I'm not getting any money from them anymore. At least I'm honest about it. Okay. Second thing is autonomous vehicle security. That's for serial machine learning. So this is really the reason why I'm here, because this is, I would say, 40%, 45% of my time goes there, and I have 5%. No, 15%. My math is off today. 15% miscellaneous projects that I'm still working on. So around half of my research efforts goes into this. And the questions I'm looking at, and we talked the majority of you in the lab already. I showed you the slide maybe. Two questions where I'm asking myself is a lot of the work so far works on object detection, perception-based attacks, right? How can we trick lane detection algorithms? How can we track traffic sign detection algorithms? Under research area, how can we attack trajectory planning, motion planning of AVs? There's one paper that's been archived 2 months ago, and that's pretty much it. Big research gap here. That's what I'm looking at. There's a ton of work you can do. Second thing is, and this is more like a long-term vision thing, a lot of the research in this area, not only in security conferences, but also like CVPR and NIPS and whatever, is on attacks. Because people really like to see attacks, right? They want to see, okay, what can go wrong? Theoretically, there's so much that can go wrong. There just needs to be people working on these attacks. But for the industry itself, and I have a lot of, due to my industry connections, I have a lot of discussions with GM and Ford and all these car makers now, BMW, and what we're asking ourselves, or what they're asking themselves, is, okay, you work on this stuff, which is cool. You try to break our stuff, and we can have money. Great, do it. We want to see actually what's going wrong with our products. But what they're really interested in the long run is, how do we do it? Is it like, do we train better models? Do we just collect more data and throw it and retrain our models? Is that what we should do, or what should we do? And I'm saying, okay, use sensor fusion, and don't only do sensor fusion of LiDAR and camera. There's even papers that trick the sensor fusion of LiDAR and camera. So security is always an evolving thing. Like, if you really want to break something, you will break it. And the question is, how do we make our stuff, our models, or our cars more robust, our perception systems, our motion planners more robust? And I'm saying, it's okay, you look at sensor fusion, maybe of LiDAR and camera, and like all these advanced sensors that are exposed to the environment. They always get something out from the environment. And obviously, an attacker can also try to spoof both or trick both of these same things at the same time. But why don't you use like in-vehicle network and data? That's not really like, taking stuff out from the environment, but it's like inside the vehicle, generated inside the vehicle. Automotive specific side channels. So this is something I want to look into. I think this is more like a very long-term vision. First, we need to look at more attacks, try to understand stuff better, and then because the entire area is very new, 5 years old maybe. So there's still a lot of work to be done. So yeah, thank you. And well, contact information here. I can circulate the slides. That stuff is also recorded. I'll also share the recording with you. Just some advertising here. If you go to my website openings, I do have openings. I think I've mentioned it a little bit to you as well. So I'm looking for 1 to 2 PhD students, obviously from the audience here, mostly in the latter part. Autonomous vehicle security, CV experience is a plus, specifically looking for computer vision people. But if you would say, oh, I really love like hardcore security, and I'm a network security, I'm a cryptographer, and I want to work on Android, or feel free to do that as well. Like I'm always looking for good security people, like real security people as well. But if you're doing computer vision, if you really like working on autonomous vehicles, and I've had wonderful discussions with a lot of you today, and I think security folks, they just don't have the computer vision experience. They try to break something, they try out something randomly in the simulator, and then they're like, oh, it broke, it misclassified this. And then you ask them, why did it happen? They're like, what? We don't know, it's black box to us, It just happened. And the security folks love to see that, don't get me wrong. But what I want to do is I want to have it also like, explainable AI. This is also like a really cool research direction that a lot of people are working on right now. Why did we break this? Why did this happen? Or how can we make a little bit more carefully crafted adversarial examples? Or how can we trick the models in a more careful way so that, even if you train a model, retrain a model, that it's still very hard to break or very easy to break, right? So basically the opposite of robust ML. Right. And I also, one more thing. So it's all on my website. I just took a screenshot. But one more thing is I also am looking for undergrads. So if you're an undergrad in your 3rd year, have 1 year left here, and are working with Dr. Gunal here as part of her lab. And if you want to keep working with her and want to collaborate with me, I'm really happy to have you in Clemson over next summer for 3 months. You can make 2.5, maybe 3.5 and flexible. You will get your visa by our international services center. I will pay you a little bit more money. It's limited funding, so I can't take 10 students, but there's some funding available, and then we can collaborate and work and write cool papers. And if you really like Clemson and the work that we're doing, you can apply for the year after and come join my lab. All right, cool. Thank you.